now.
This meeting is being recorded.
Thank you so much for joining, everyone. We are doing an engineering showcase with the James Webb Space Telescope engineers tonight from NASA. It's a super exciting event and really, really excited to get some of our amazing questions answered all about the James Webb Space Telescope. So tonight, if you have any questions, like I said, please put those in the chat. We will try to answer those for you. And we will have a section for question and answer at the end. So keep your questions in mind for our amazing guests today. For those of you that are participating in eCYBERMISSION this year, thank you so much for joining. We are really excited to see your amazing STEM projects. We know you're doing a great job. And tonight our goal is really just to inspire you all to keep learning about science, technology, engineering, and math. So sometimes we could all use a little bit of STEM inspiration. So my name is Lauren, and I'll be your host this evening. I work with eCYBERMISSION, and I'm joined with some amazing eCYBERMISSION staff. We have Carrie, Faith, Catherine, Winnie on this evening, so they'll be answering your questions in the chat. If you have any questions, you can also email them to missioncontrol@eCYBERMISSION.com, and we will be monitoring that this evening until midnight. Today is an exciting day. It's the last day of our registration. So if you haven't finished your registration yet for eCYBERMISSION, don't forget to do that this evening by 11:59 Eastern Time. All right, so let's get started. We're going to jump right in. We have some really special guests this evening. We have some from NASA and the James Webb Space Telescope team. So we're going to be learning a little bit about what it's like to be a NASA engineer. And we're going to learn a little bit more about James Webb Space Telescope. So on your Zoom screen, you'll see a little icon that says reactions. Give me a thumbs up reaction if you've heard of the James Webb Space Telescope. Okay, cool. I'm seeing quite a few reactions here. If you have not, give me I don't know, just pick a reaction to do. Okay, we're going to learn a little bit more about it this evening. So to start us off, I'd like to welcome our first engineer, Sandra Irish, to open our conversation this evening. Sandra, thank you so much for joining. Can you tell us a little bit about yourself and your experience as an engineer and what it's been like to work on the James Webb Space Telescope?
Okay, well, thank you, Lauren, very much. My name is Sandra Irish, and I do work at NASA Goddard Space Flight Center, which is in Greenbelt, Maryland. And I've been there for 38 years, and I absolutely love my job. It's very exciting. Every project that I've worked on has just been a challenge and been very interesting. So if you go to the next page, I guess I can talk a little bit about myself. So there I am, standing next to a 1/20th scale model of the deployed James Webb Space Telescope. This picture was taken just this past year in the summer. And I was there at Northrop Grumman in California, Redondo Beach, California, doing my job there at the time. And so I hold a couple of positions at Goddard Space Flight Center. I'm a group lead for Mechanical Systems Analysis and Simulation branch. And so generally I'm responsible for mechanical systems. For James Webb Space Telescope in particular, I was the lead structures engineer. And what that basically means is I was responsible for the mechanical analysis and all the mechanical testing for the launch environment and also on on-orbit mechanical performance, which has to do with thermal cool down and jitter measurements. So I had a large team of people working with me in order to accomplish this task. So I've been at Goddard for 38 years, and out of that 38 years, 16 on the James Webb Space Telescope project. And so people say, wow, how can you be on one project for 16 years? It's because it was very exciting. There was never a dull moment. It was very challenging. And so it just, kept my interest the whole time, and I really wanted to see it through. And you may think 16 years is a long time, but honestly, there were some people on the project even longer than I was. So it really was an exciting program, and I'm glad to be a part of it. I am married. I am married to my husband, who is also a computer engineer. I have 2 children. They are 23 and 29 years old, and they're also computer engineers. So sort of a family of engineers. And I do some of my hobbies when I'm not doing engineering is I love to dance. I've taken all kinds of dancing all through my life. And I'm a gardener, and I also am a youth group counselor, and I love arts and crafts. But probably the thing most people think of me of is I'm a huge soccer fan. So used to play, used to coach, and I coached my children. I was a ref. Now I'm just a big fan. So that's a big part of my life is soccer. So a little bit about myself. Okay, the next one. So a lot of people want to know my career path. How did I get to be a NASA engineer? Well, when I was in high school, I really loved math. That was my favorite topic. Always interested, just loved it. And so that, as well as science, was my area that I enjoyed the most. And so I decided to I also loved being around airplanes. I used to go to the airport as a young kid and watch the airplanes take off and land. I know people might think that's a little crazy, but I really enjoyed it. They were fascinating to me. And I started at the University of Maryland in College Park. And that's their logo there. They're the Fighting Terrapins. And I studied aerospace engineering. I got my degree, Bachelor of Science degree in aerospace engineering with an aerodynamic focus. Yay, go Terps. I thought I was going to design airplanes, but then my career took a different twist. I ended up sort of studying structural dynamics in college, and the professor that I worked with was a NASA engineer, and he said, "You're really good at structural dynamics." I said, "Yeah, I really love it." So he asked me to come work at NASA, and I've enjoyed it ever since. And some of the programs that I've worked on before James Webb is the Cosmic Background Explorer, which found the first light of the universe. I worked on a Japanese mission called Astro-E and Astro-E2. I worked on upper atmosphere research satellites. So I've worked on telescopes as well as Earth observing satellites. And I guess Lauren asked me to tell you a little bit about my typical day as an engineer. And it sort of depends on the phase of the program. If you're in the early phase, you do have to be at the computer a lot with a lot of design calculations. And then once you come up with the design, then you have to start to build and test. And that becomes really exciting because then you go out in the labs, you go in the test facilities, and you see everything that you've designed and making sure it works. And the testing phase is very long days and a bit stressful, but it's really exciting as well. So you get to do a little bit of all of that. Okay, next one. So I just was gonna flip through these pretty quickly so you can see a little bit about what I've been through the last few years on James Webb, pretty much in the testing phase where we have the hardware. This picture here was taken at the Goddard Space Flight Center. I'm in front. I was in charge of this big group of dynamics engineers, and we were testing the big screen behind. You could see these yellow ladders up and down, and there's a big tent, and behind there is the James Webb Telescope. It's hard to see in this picture, but that was the real thing that's up in space right now. We were shaking it to make sure that it would not fall apart when we launched on a rocket. And then on the picture on the other side, you could see me with some of my team members. we were doing acoustic testing. So if anybody's ever seen a rocket launch, very, very loud, kind of louder than even going to a rock concert, just extremely loud and a lot of motion. And we had to make sure that our beautiful mirrors on James Webb would not fall apart and that would stay in one piece. So that was the testing that we did. So the next one, you can see what after we finished mechanical testing, we brought the telescope to Johnson Space Center in Houston, Texas. And there's a picture of me with one of the integration engineers. We just moved the telescope into the clean room. And that's what we were standing outside there. And then we lifted the container, lifted the cover off the container. And you can see in the other picture down below a picture of our beautiful telescope in one piece. That was a very exciting picture for me because that was the first image that I got after we transported the telescope to Johnson. And that was, to me, that was exciting because I wanted to make sure everything was okay. So the next picture, the next page, this is a picture jumping ahead a few years. We test in many different levels, and this is the entire observatory. So what you see there is the entire James Webb Space Telescope in what we call our launch configuration. As many of you know, we fold up into the top of the rocket in order to fit in the top of the rocket. And once we get up in space, it took us about 2 weeks to completely deploy into the configuration it is right now, where we have to, where we will be taking data. So when we are in the rocket, this is the configuration we will experience loads. So it's sitting on what we call a vibration shaker, which imparts mechanical load to the telescope so we can make sure everything stays in one piece. So I'm in one of those people in the white bunny suits, we call them, contamination suits, and Elaine, who's also going to be on this talk, she can tell you more about that because she is a lead contamination engineer. But we had to make sure we were clean at all times because this fancy telescope is like a camera. And if it's dirty, it will not take good images. So we had to stay clean all the time. The next page. So here's a picture of me. After we finished vibration testing, we deployed the entire telescope at Northrop Grumman in California just to make sure everything was working after the vibration test. So there's a picture of me, and the sun shield is open there in that picture. On the right was one of my farewell pictures to the telescope at Northrop Grumman before we packed it up and brought it to French Guiana. Next one. Here is, I was a mechanical lead in charge of transportation because if many of you have driven in a truck or a car or an airplane, you know that when you're in these vehicles, they move around quite a bit. And our telescope could not move. It had to stay in one piece. And if it moved too much, it would go out of alignment. So our job was to verify that it would stay together during transport. And those are some pictures showing us the telescope. The entire observatory is inside that white container. And the very bottom picture was taken at Northrop Grumman in California. There's a big truck that's pulling the container. The maximum speed that we would drive, that container was 15 miles an hour. Most of the time we were driving at 5 miles an hour. So very slow and careful. It took us all night to travel from Northrop Grumman in Redondo Beach to Seal Beach Port near Long Beach, California, which is normally, if you got in the car, would take you about 20 minutes. But our hardware took us all night to get there. So that's how slow and careful we drove. Next one. So this is a picture of me with one of my teammates in front of the MN Colibri. This is the ship that took the container and with the observatory to French Guiana. You can sort of see in the back to the right is the container. You can see the green truck pulling the container and how small it looks next to the Colibri. The Colibri was a very large ship. We contracted it from the French government. So they were really great and very careful in taking our container and our observatory to French Guiana. Next page.
We did get a great question from Elijah. What did it look like inside of the container? Was the telescope just folded up like it was in the picture before?
Yes, it was folded up just like in the picture that I showed you a few pages back. The same configuration that it is for launch, but it was on its side. I don't know if I might have a picture at the end to show you when we have to rotate the observatory from the vertical position to sideways to fit it inside the container. This is a picture of me inside the ship. When we brought the container in, one of the jobs as a mechanical engineer is to lash the container down to the floor of the ship. And you'll see many, many chains holding the container down. Again, if you've ever been in a boat, you know that the boat goes up and down from the ocean waves. We had to make sure that container would not move. So we had to lash it down with all those chains that you see all around, so it wouldn't move during the ship voyage, which took about 2 weeks through the Panama Canal. Traveled down the coast of California, through the Panama Canal, along the northern coast of South America to French Guiana, which is a country right near Brazil in South America. Next page. Here's a picture of my one of my colleagues. The one on the top left is me and my colleague. We were on a bridge, and behind us is the MN Calibri ship, and our observatory is inside there. So we stopped to take a picture. This is as it approached the port in French Guiana. On the right is me talking to the ship captain. I talked to him when I was at Seal Beach, and we had a long discussion about how careful he need to navigate his ship in order to take care of our baby. We called the observatory our baby. It's $10 billion worth of hardware that we wanted to be very careful. So he was very willing to talk to me. He was very willing to maintain navigation through very low waves and low, what we call sea states, in order to keep the loads to a minimum on the container. So this is a picture as soon as he came off the ship. I was so excited to see him, and I thanked him for everything. And it was just wonderful to be able to talk to him. And then the next page is showing after we came out of the container, the picture on the right is showing the observatory moving from the horizontal position and rotating up to the vertical position, which we had to be horizontal for shipment and vertical for launch. So the picture on the right is me saying goodbye to the observatory in French Guiana. And I ended up coming home after that picture. So that was the last time I saw the observatory before it went for launch. So I was very successful transport. I was very happy. Nothing broke, nothing moved. And then it maintained that position through launch, and then it did not start to deploy until we got up into space. So that was a few pictures of my experience on James Webb.
Thank you very much. So much. That's amazing. We have a question in the chat that just came in that I'm sure you can explain. If a telescope like this is so big, how does it fit into a truck? And I believe it's just because of all the ways that it folds. Is that correct?
Yes, the picture that you're seeing, that is its folded, that is the folded, or what we call our launch configuration. To fit in the container that's being pulled by the truck, we had to turn it to its side, and we fit it very carefully inside the big white cylinder that you saw in some of those other pictures. And we had to maintain clearances, and we had to give it also isolation so it wouldn't move. So we were able to accommodate it in its launch configuration, but not vertical, horizontal.
Thank you. And we'll definitely have some more time for Q&A at the end, but we did have a couple that I would love to get answered really quickly. We had a question that came in from Dalen about how long it took to unfold once it got to space.
2 weeks.
Wow, that's
2
amazing.
weeks. Yeah.
So cool. Wonderful. Well, thank you so much, Sandra. I loved seeing that insider view into the James Webb Space Telescope. What an exciting project. And thank you so much for all of the work that you've done on it. We loved hearing from you. And we'll hear a little bit more from our next engineer, Elaine Stewart. So Elaine, if you could go ahead and share a little bit about your experience working on the project.
Absolutely. So I wanted to speak a little bit about, my start at NASA. I actually pursued my chemical engineering degree at the University of Delaware, and I decided to pursue engineering because I was really passionate about math and science, and picked chemical engineering because I didn't really know exactly where I wanted to go with it. I came across internships at NASA and decided to apply. So I actually received my first internship and spent the summer after my freshman year of college at the Kennedy Space Center in Florida. There is a consortium called the Space Grants, and many different states have this. So they actually funded this internship at Kennedy. And this summer, I actually investigated what different components exist in lunar soil and how we might be able to actually use that on a mission to Mars. So here you can see in this left picture, these are the doors that I got to walk through every day when I went to work at Kennedy. And this is actually the same location that the astronauts used to walk out of before they got into the Astro van and they went over for their shuttle launches. So I felt really inspired every day walking through these doors and knowing that so many heroic and talented people like astronauts had actually been in the same space. And here you can actually see on the right, the vehicle assembly building. So this building is where they actually stack the rockets and assemble them at Kennedy. But this first internship really clued me into the fact that I wanted to have my career at NASA. And if you go to the next slide, please. I applied to an internship that is kind of like, if you've heard of a co-op. So I was able to actually work at NASA while I continued my degree at the University of Delaware. So NASA has a program called the Pathways Program, and I was accepted to be a contamination engineer. So in my group, we actually have chemical engineers, we have material scientists, biologists. There are many different fields that are applicable to contamination engineering. And our main purpose is to really try and protect the hardware. So those beautiful gold mirrors that you saw on the Webb telescope, we need to keep those mirrors as clean as possible so that we get the best images possible back once we actually get to orbit. Here you can see a picture of myself during my first summer at Goddard. And as Sandra mentioned, every time we go and interact with the telescope, we have to wear these special garments or the clean room suits. Now, lots of you have been wearing masks for COVID. We have been wearing masks for years and years. As you can imagine, sometimes you take your mask off, you have to get a new one because it's dirty. Can you imagine if all of that got on our special spacecraft hardware? So we have to protect our face, we have to protect our hands. We wear all the way from head to toe special garments in order to make sure that while we are performing our work, we are not getting the telescope dirty at all. And the next slide, please. Okay, so this video, once it starts playing, it's okay. Sometimes it's a little slow. Okay.
It's loading, sorry about that.
No, it's okay. Okay, perfect. So to talk a little bit about a day in the life for me, here is a short snippet of it. So we gown up, we go into the clean room, and we're really supporting all of the different disciplines that work on the telescope. So we'll support Sandra's mechanical and testing group, we'll support the thermal engineering group, And we're trying to make sure that all of the operations that need to happen on the telescope are completed in a clean manner. So there are some times where I will have computer work to do. This can involve reviewing procedures of what work will be happening in the clean room. We will track and analyze the amount of particulate. So we have special samples that we place around the clean room to monitor what the fallout looks like. So we're really trying to count, you know, how many particles are on it so that we can identify what our surfaces look like on the telescope. Okay, and next slide. So on top of the project just being really an incredible engineering challenge, it was also an opportunity for us to travel. I was able to travel and follow the telescope from Maryland to Houston, Houston to California, and then to French Guiana. So I did see a question in the chat asking why French Guiana. Now, the Webb Telescope mission has been going on for many years, and it was decided quite a long time ago that the European Space Agency would give us this rocket in exchange for observation time. But on top of that, this was the rocket that we could fit in. Even after folding up, the Webb Telescope is still such a large observatory that we needed a very special fairing, which is this top part of the rocket that the telescope actually sits in. So here on the right, you can actually see the Ariane 5 rocket. This is a full-scale model of the rocket that we ended up using to launch the Webb project. And on the left here, you can see the control center in the Jupiter building at the French Guiana launch site. And this is actually where the head of ESA sat during our mission launch. So yes, I'm very happy to talk to you. Thank you so much for having me, and happy to answer any questions at this time.
We did get a couple questions about the telescope. Carissa asked why the mirrors are gold.
Okay, so we are actually trying to perform observations in the infrared wavelengths. And in order to actually observe these targets, we need to have reflective mirrors. So if we're looking at a target of observation, you know, say a galaxy, we're actually able to reflect the light that we see, and it goes from the primary mirror to a secondary mirror and then into the instrument. So that is actually how we perform our observations, and then we can analyze and process the information. So it needs to be reflective so that we can actually make our observations while we're on orbit.
Awesome. And we got a question from Milan. How do you prevent the telescope from falling off the stand when it's diagonal?
Maybe this is a good question for Sandra, yes.
Yeah, so that's a really good question. So what we designed for is the interface between the observatory and the stand was held down by 48 bolts. And so what we do is we verify that the strength of each bolt. We make calculations based on the mass, the center of gravity of the observatory, and how much load would be on every location. And then we choose certain bolts, very large ones in this case, that we used in order to tie down, and we also have to determine the proper torque values for every single bolt. And based on our calculations, we verify that it can support the weight of the observatory. But we always do at NASA, one of the things that we do as NASA engineers is we have what's called redundancy. So if we lose one or two bolts, we still have enough load that the rest of the bolts can handle the load of the observatory. And the other thing we do is as NASA engineers is we do a lot of testing. So before we use the interface hardware with the actual flight observatory, we use mock-ups. We build a mock-up of the observatory and we test the observatory, the stands. We test everything with mock-up hardware and to verify, and we go through all the operations. we verify that we can handle all those loads. And we do that before the flight hardware touches any of the stands and any of the operations. So that's a really good question.
That's fascinating. Elijah wants to know, what is a mock-up?
Mock-up is something that doesn't necessarily look exactly like the real hardware, but it has the same mass and center of gravity, and it's like a practice. So if you build something to hold it, it could be like a box, it could be like a big cylinder. In this case, like James Webb, when you see it on the stands, it looked like a big cylinder. So what we made is a really large, big metal cylinder. So it's an example of what the real hardware might look like. And then we use that to test all of our stands and all of our equipment and practice all of our operations.
Thank you. We're getting such amazing questions, y'all. Keep them coming. Kayla wants to know, how does the telescope stay in the spot that you want and not drift off into space?
Okay, so what I will tell you is right now we're in what's called the halo orbit for L2, which is the Lagrange point 2. It's 1 million miles away from Earth. It's in an orbit that will rotate around the sun, and the Earth will always be behind it. So in order to stay in that orbit, we have little thrusters that we use, a little bit of fuel. We carry 2 big fuel tanks on board, and the thrusters will release and fire and maintain the observatory constantly into that orbit. And we're carrying enough fuel on board to meet our science objectives. The goal is 5 years. But I will tell you, we've done such a great job with our tank design, our fuel design, and as well as the orbit insertion from the Ariane space, that we have over 20 years of life that we can have for science for James Webb, which is really exciting.
Awesome. So that kind of answered one of our questions, which was, will the satellite be there in space forever? Will the telescope be there forever? So it's looking like you have between 5 to 20 years.
It will be there forever, but it will be taking science for at least 20 years.
That's amazing. Another question from Alexander. How long did it take to build?
The project actually started, I believe it was around 1995, 1996 in the very first initial stages. The COBE mission that Sandra mentioned was one of the projects that she previously supported, was led by Dr. John Mather, who is our project scientist for the James Webb Space Telescope mission. And he actually won a Nobel laureate for the work on COBE and their studying of the cosmic radiation and the background for that. So James Webb has been a concept that was in development for quite some time. And the way that these big flagship missions work is there's a decadal survey that is conducted every 10 years where there are experts in the fields of astronomy that get together and figure out what are the big questions that they want to answer. And then they pick projects that will support the questions that they want to answer. So Webb was actually chosen for a mission as part of one of the decadal surveys many years ago, and has been in development and evolved as they engineered how we're actually going to make this mission happen.
Amazing. We're getting so many great questions in the chat. I'm going to try to get as many as I can. We have one from Elena about how is NASA able to control like the thrusters and the orbit from Earth if the telescope is so far away?
Well, we're doing that through in Baltimore at the Space Science Institute. It's our mission ops center. They're able to send commands to the observatory from Baltimore. It's been working really great. So far, so good. They can, we have our solar arrays out and we're drawing power. We can send commands to our attitude control system components. We can turn on electronics to the plus side, or 2 different sides, redundant sides. We can also do what's called slewing. So based on our attitude control system components, we can send commands and they can adjust the telescope so that the sun shield is always facing the sun. And we can adjust it if we want to search for a star or certain parts of the sky. So that's pretty, I think most of that is pretty standard technology that we can do with other satellites. And being so far away has not been an issue at all.
Great. Anish is curious. I know you just mentioned a sun shield, but Anish is wondering what would happen if the telescope was facing the sun directly from where it is.
Oh, we had to actually protect the telescope. There is where the instruments are actually housed. There is an opening that we had to have covered because we couldn't even have it exposed to like the light of a flashlight or just regular light in a room. Because if you think about it, we're trying to look at very faint targets. So facing the sun would be very detrimental to our instruments.
Yeah, great questions, everybody. And feel free to keep those questions coming. I'm just going to move a little bit ahead to our next image, which is a really cool picture of the project that we're talking about. But if you guys have questions that you'd like to ask, you can raise your hand, you can unmute yourself, or you can keep those going in the chat. We do have a couple more minutes to get to chat with our experts. We did have a question from Daniel about what is the key to making a rocket fly?
I would say it's the giant solid rocket boosters, the engines. So we have huge fuel tanks. It requires a lot of fuel. So it's big engines and a lot of fuel.
And Nathan is wondering, what discoveries are you hoping to make with the James Webb Telescope?
That's a great question. There's 4 basic science, checking for first light, looking for new planets, and the one that I'm most excited about is new life. So one of our instruments, we have 4 instruments on James Webb. One of them, the near spec, is a spectrometer. So what's exciting about the spectrometer, it can tell us not only what we are imaging so we can see, but we can also, they can tell us what it is, what are some of its components, carbon, oxygen, hydrogen. So what are these elements that they're actually looking at, which is exciting because knowing the elements, we can know if there's any potential life that's there. So that's actually one of my most exciting thought is there life. I think a lot of the scientists are looking at exoplanets, which are other planets that they expected not to see, but with James Webb, with its precision, it's going to be able to see much farther away than we've ever been able to see before. And it's going to be able to see things that we've never been able to see before. One of the things about Hubble Space Telescope, it's a visible telescope, but James Webb is infrared, so we can see behind clouds and we can see behind gases to see bright objects, which is exciting. So even compared to Hubble, which, the same image James Webb can see with much more clarity. So there's probably some planets there that we didn't even know about, or stars. So that's what the scientists are most excited about seeing.
2 questions from that. Alejandro is curious, what are exoplanets? And Kayla wants to know, have you ever seen any signs of new life so far?
Yes, not yet, not with James Webb, but other satellites have seen carbon and water, ice, on other planets and other moons. So there is life out there, and we are seeing it with our satellites and our telescopes. So exoplanets are a type of, I'm not a scientist, so I might get this wrong, but I'm not a scientist, but it's basically planets that sort of orbit other planets. That's the way I understand it. I could have that wrong because I'm engineering, but I don't know if you know, Elaine.
No, yeah, I think that's the perfect explanation. Basically, just a planet that orbits around another star. And back to life identification on other targets, I would encourage everyone to look out for information about Europa. I think Europa is a really exciting object that NASA has been investigating, and they think there's actually kind of like icy oceans on Europa, which is really interesting to investigate further.
Just so you guys know what you're looking at, I hope you understand what you're looking at. Right there, there's 6 of our 18 mirror segments that make up the primary mirror for James Webb. And this picture was taken at I believe it was at Marshall Space Flight Center, the XRCF chamber. So here what we were doing is we were cooling down the instruments and making sure that they could survive their cold operation temperature on orbit. They operate somewhere between 35 and 60 Kelvin. So we had to really test them. Each segment was tested prior to its assembly into the entire primary mirrors assembly, which was all assembled at Goddard Space Flight Center, where Elaine and I are home based. So, but what we're seeing there is just a giant chamber, and this chamber allowed us to test 6 at one time, which was great because we had a lot of mirror segments to test.
That's amazing. We actually did have a question come in about that. Christopher was curious why the mirrors are hexagon shaped.
Yeah, we get that question a lot, actually. It's all based on the optical design. We wanted to go bigger, and it's a 6-meter primary mirror, and it would just not fit in any kind of launch vehicle. So we knew from the get-go, if we wanted to launch a 6-meter primary mirror into space, it would have to be, something that could be folded or bended in place. And so this type of construction with the hexagons makes that very easy to do. And it worked very well from an optical point of view as well.
Awesome.
So, and what's really fascinating to me, and sort of was a lesson learned from the Hubble, as a mechanical engineer, one of the things that was done is every single one of those mirror segments are adjustable in many different directions. So you can translate them up and down, sideways. There's even what's called a radius of curvature. So the surface has a curvature, but if it's not exactly correct, we have the ability to adjust the curvature of the mirror on orbit. So that's really exciting to me because I know all the mechanical behind the mirror, which you often don't see, is actually more fascinating to me than the shiny gold surface, because behind the mirror is what makes the mirror work with these fine adjustments that can be made, which we call Hexapod Actuators, which allow, and radius curvature actuators, which allow for this bending to occur. And we can do that from the Mission Operations Center in Baltimore, sending commands to the mirrors up in space.
Yeah, and that's one of our main activities for the next couple of months. Really, we need the primary mirror, all of these 18 segments to work together to function as one big mirror. So now they're working on basically calibrating and moving the mirrors as they need to before they're ready to get those first light images that we'll get in a few months here now.
That's so exciting. This project is so fascinating, and we have so many questions about it. We're trying to get through them all. Madhav is wondering, how does the the mission control process the information, and is it kind of like looking at a photo on your phone? Is it like a color image, or does it have to be decoded?
So right now, the images, it's, might be boring to a lot of people, but right now we're looking at what's called telemetry data, which is a bunch of screens with lots of different numbers. It tells us the sensors, it tells us the temperatures, it tells us the motion, it tells us the attitude of the observatory. But that's what we're getting right now as we are adjusting our telescope up in space. So it's like a fancy camera that we're adjusting from the ground up in space. And then once all the mirror segments align and they will focus on one point, then at that point we will be getting images from the instruments on their detectors, and those images will get sent to the instrument teams, who will then be they will be decoding those images along with the scientists that we have as part of the science team, and they will be deciphering what they're looking at, more so than I would be. but yeah, they will be basically like taking a picture on your phone.
That's so fascinating. And I know that a lot of the students who are tuning in tonight are working on a team. So as a team, you work on different parts of the project. With a project like this, that is so big, are there often different sides of it that you really don't know much about? And what is the communication like between the different teams working on this project?
Yeah, I mean, it's very essential. I mean, we have international partners. We have even just across the US. The telescope has been in so many different locations, and there have been people on the project that their portion of it was done many years ago. And then there are people on the project now who this is their time to shine when we're actually operating the telescope up in orbit. So what's really amazing is that it's each person coming together to make this mission possible. Something like this is absolutely not possible, even just, on your own as being one agency. We needed those international collaborators. We needed those contracting companies to help us out. And what's really amazing is that while everyone has their own specialty, we get to learn from each other. There will be some meetings where we'll have so many different disciplines. We'll have the contamination engineers, the mechanical engineers, the thermal engineers, all working together to solve a problem. And it's really essential because, you might think that you're solving the problem best for your subset of knowledge, but you might not know how that could impact Sandra's team for the mechanical testing group. And if you don't work together, then you're really in the end going to create more issues and more work than if you can collaborate and get each other, just be successful together.
Yeah, and it's very important that every discipline is heard for every problem. And if that doesn't happen, you will have issues. So especially if there's any change that happens, you need to make sure it's okay with every contamination, electrical, mechanical, thermal, propulsion. Every system has to give the okay for any kind of change, because it may not affect me as a mechanical engineer, but it will affect contamination and Elaine and her company and her group. So it's very important. There has to be a lot of communication between all the engineering staff. And then there's also the scientists and the folks who are working in commissioning. They are part of the teams as well. And the other thing I will say is when I was working on the telescope testing at Goddard, we had people coming in from Europe and Canada who were flying for and being there as part of the team. Those same people were involved in the observatory testing, but that happened in 2020 during COVID. So a lot of them could not travel to California for the test, but they were still involved, and we had to make sure that they were included and their input. So we were working pretty much around the clock at all kinds of crazy hours to get input from folks in Germany and folks in Canada and England and France in order for their inputs to be included in their review of the data. It was actually quite challenging, but they loved it and they were excited and they wanted to be a part of it. So we have had some challenges, but you have to find a way to overcome it, and you have to find a way to include everyone on your team. You will get the best product if you do that.
Mm-hmm.
It's wonderful. Thank you for sharing with us a little bit about that. I know it's definitely a challenge to communicate with people in different time zones, and especially on such a large thing, but congratulations on such an amazing project. It is so exciting to see it unfold in space, literally. And I know that we do have a few more questions. I know that you weren't able to fully test what it would be like for it to unfold in zero gravity. What was the testing like pre-launch, actually unfolding the mechanism?
So I can answer some of that from a mechanical point of view. So after we test kind of like we fly, and that's really important. So what was it really going to happen? What was going to really happen? The first thing is we were going to be on top of the rocket. We were going to shoot up in space, which is a lot of mechanical vibrations and load. Then once we get into space, space is really cold. We're going to start to cool down. And as we're cooling down, we're going to open up. So what we did on the ground is the first thing we did is we were in launch configuration. We went through vibration and acoustic testing. Then after that, we brought it into the clean room and we started to open everything up. Now, one of the things we couldn't do on the ground was open everything up cold, because as you're in space, things start to get cold. So we opened everything up in ambient temperature. But what we did before the big observatory is different pieces went through cold vibration or cold deployments. So we did measure, we did check out things cold at the smaller levels of assembly. But once we got to higher levels of assembly, it was very difficult to do that. So as Lauren correctly stated, we couldn't really test it cold at the all-up observatory level. So that was the first time done in space. So we were very excited. But we did do lots and lots of, we did as much testing as we could on the ground, and we did do testing cold at smaller levels of assembly. So we were comfortable with what we did with the method that we used.
Thank you for answering all of our questions. We really appreciate it. We have just a couple more minutes, and this is a good one too from Kayla. Kayla is wondering, as an engineer, if you ever hit roadblocks and feel like you can't keep going, and if that happens, how do you overcome that?
I mean, there were definitely lots of challenges that came up with the project, but we work with many inspiring people, and Sandra and I both are people that want to keep, find a solution and push forward. And when we hit those roadblocks, we're almost excited to try and figure out a solution. So creating a telescope like this, where we're developing new technologies, and it's, the largest telescope of its size that we've actually been able to launch to this point. It makes sense that you're going to run into some problems along the way, and, challenges, just even time zones or transportations and everything, they did come up, but I really think that it was the team that kept everyone going, and knowing that we were going to be able to get these amazing images and perform some really incredible science that at the end of the day, we all wanted to work towards and work together for.
You have to believe in the outcome, and you have to be motivated. And I think everyone on James Webb was motivated to find a solution. As engineers, that's what we do. We solve problems. So to us, that was just fun and challenging. But dedication and motivation, and that's how we got through. Coffee, a lot of coffee.
Awesome. We have time for about one more question from Anish. And this is, I heard that the Webb telescope can basically look back in time. Can it look at the Big Bang?
Yeah, so that,
yes, I guess the answer is
yes.
yes.
That's actually one of the, oh, go ahead, Sandra.
I was just going to say that's one of our 4 main science goals, and we call it First Light. It's kind of a continuation of what we learned from the Cosmic Background Explorer. And as Elaine mentioned, Dr. Mather, Don Mather, is the same scientist from the Cosmic Background Explorer as it is for James Webb Space Telescope. He is our lead project scientist. So he was interested in continuing the observations of the background and to see if there is more they can learn there about the Big Bang and First Light.
That's so exciting. Well, thank you so much for spending time with us this evening, sharing your photos, your experiences, and answering all of our questions. We really, really appreciate it. And congratulations again on such an amazing project. Thank you for the work that you're doing to make the world a better place. Everybody who joined tonight, thank you for joining. If you have any questions, you can send them our way. Just email missioncontrol@eCYBERMISSION.com. If you are wanting to join our next live chat, it's going to be on Wednesday, February 9th. And we'll be having some special guests from Rose Holman Institute of Technology in the ROTC program. And we'll also be welcoming some cadets from West Point. So come and join us on our next live chat on February 9th. And thank you so much for all that you do. Hope you guys have an amazing evening, students. Good luck on your projects. Don't forget today's the last day to complete your registration, and go forth and be inspired with STEM. Thanks everybody. Have a great evening. Thank you, Sandra and Elaine, so much.
Thank you.
Thank you, Lauren.
Bye.
Bye.
Thank you.
Thank you.